or other lectures, we have looked at the numerical approach to solving plane stress, combined loading plane stress, complex stress situation, where we get up to these two equations here. Okay, so we have sigma x prime given by equation 9.1 here, and tau x prime y prime given by the next equation 9.2. And after that, we modify the equation to find the principal stresses or the maximum and minimum normal stresses. And we also found an equation to find the maximum shear stress. Okay, basically this square root at the bottom is the maximum shear stress. Now these two equations, if you look at the mathematical approach, can be combined and rearranged to come up with this equation here. If you notice, this is an equation for a circle. Okay, and in this equation, sigma average is the same sigma average we were talking about in the last lecture, and R is equal to tau max. This equation here is tau max, right? That is the maximum shear stress. So this circular equation then can yield a circle. So when we talk about Mohr's circle, it's actually a graphical approach. Instead of having to solve equations like this, we can use the graphical approach to solve for our stress transformation. Okay, this is an example of a Mohr circle. Now, if you notice clearly, the horizontal axis is normal stress, right? And the vertical axis is the shear stress. So you have normal stress here, normal stress, and you have shear stress as the vertical axis. The other thing you have to observe carefully is that the shear stress axis have a positive value downwards. If that is 0, 0, the origin of the graph, shear stress is positive downwards. Okay, while upwards it is negative. So if you look at our stress element, right? So our stress element, sorry, we draw our stress element in the positive direction of all the stresses that we possibly could have. So we have sigma x, we have sigma y, and then we have shear upwards, right? And downwards. And then we have complementary shear on the top and bottom surfaces. So this is tau xy. And if you look closely, tau xy on the right surface and the left surface is forming a counterclockwise couple. Okay? And that is positive tau xy. So in certain textbook, it's written here as CCW, counterclockwise. And the top here is written as CW, or clockwise. So to help you determine location of the point based on the shear stress values that you have, so either you look at the values as positive or negative values, or whether it's clockwise or counterclockwise. So positive couple will be counterclockwise, negative couple will be clockwise. So in this example on top here, on the x plane, the couple is counterclockwise, so it's positive. While on the y plane, y up there, right? On the y planes, the couple is clockwise or negative. So there are two approaches to actually draw the Mohr circle depending on which textbook you follow. Now, this diagram here is based on Hibbeler. Now, what it says is we use the centroid of the circle. We find the centroid and you find the initial point. So that is normally called point A, which is the stress condition on the x-axis. So we have the x-axis there, right? And if you look at the Mohr circle closely, you will find several things. Number one, the average normal stress is giving you point C. Okay, point C is based on the average normal stress value. This is 0 on the left, so average normal stress will give you point C, right? The other thing is the radius of the circle is given by r, or this is equal to tau max, right? So we know that tau max is the radius of the circle. And so the largest value for that is down here and also up here, right? Except that at the bottom here is positive and on top is negative, but the magnitude is the same. Okay, magnitude of this point at the bottom is the same as magnitude of the point at the top. The direction is different. Okay, one is positive, one is negative. The other thing that you can notice from this graph is that since the horizontal axis is the normal stress, the largest or maximum normal stress values will be the point on the horizontal axis. Okay, and the smallest value for the normal stress will be on the point on the left of the circle on the normal stress axis or the horizontal axis. So in other words, this point here is sigma max, or if you follow other textbooks, it's written sigma 1. And the left here is sigma mean or sigma 2. Okay? So you have sigma max, sigma mean, you have tau max here, tau max, which is positive. And on top here, you have minus tau max. Okay? So you can see clearly the values and where they sit in relation to each other. Now, why is this important? The other thing that you have to remember is that angles measured in the Mohr circle is twice the actual angle. Okay? For example, this angle here is written as 2 theta p. Now, this point A is for the stress on the x-axis. So that is the reference. So this line here, AC or CA, refers to the direction of the x-axis. So if our x-axis is the reference, now from the x-axis direction, going towards the principal stress 1 or the maximum normal stress, you have this radial line here, right? Now that radial line represents the location of the plane where you can find the maximum normal stress in relation to the reference axis, which is x. So A refers to x-axis. Okay? So what it says here from the graph is that the axis for principal stress 1 or maximum normal stress in this diagram here is counterclockwise from x-axis. how much it changes is given by this angle. So it's 2p, 2 theta p. So if we draw x, right? Therefore, x prime, that line there, is counterclockwise, and the angle is theta p, half the angle in the Mohr circle. Okay, then we can draw the stress element, or somewhat we can draw the stress element orientation, okay, where we can find the maximum normal stress, sigma x or sigma max. So sigma max is here. So here you can find sigma max. So we have sigma max or sigma 1, whichever we want to use. So over here we have sigma max, right? And 180 degrees away, there is the line on the left here. The radial line is 180 degrees from sigma max. In real life, it is 45 degrees, right? So that's 45 degrees, 90 degrees. Not 45, it's 90 degrees, sorry. So you have sigma mean, which is 180 divided by 2, so you have 90 degrees, which tells us that on this plane now we have sigma mean. And so this as well, sigma minimum. Okay, so that is how useful this Mohr circle is, to help us visualize what happens to the stress element and where we can easily find the maximum and minimum stresses are acting, right? And you won't make a mistake. So we have sigma max and sigma min. And the other thing you can notice is, at the point where we have sigma max and sigma min, it is on the axis of normal stress. And the axis of normal stress is 0 value for shear stress. So we know that on this axis, both x prime and y prime, where we have max and min normal stresses, we do not have shear stress, right? So that is how we read the Mohr circle. The other thing, we can find that tau max is down there, positive tau max, and negative is up there. So the radial lines, so if we draw a vertical line here, it's a vertical line, sorry about the curve that I drew. The vertical radial lines will be the location of the plane where you can find tau max. Now if you look at the coordinate of this point, the coordinate is tau max, and then you also have sigma average. So that gives you the coordinate of that point. Okay, so it's not 0, it is sigma average for the normal stress. Whereas the coordinate for this point is sigma max, and 0 if you are looking at coordinate for the point. And that 0 is the shear stress. So for this location here, it tells you that when you have maximum shear stress, you are bound to have normal stress on all the plane, because here it is sigma average. On top here, the coordinate also is sigma average and minus tau max. Okay, so the value of the normal stresses are the same for both planes, and that's how we can determine how to draw it. And if we want to find the angle, is this angle here. So if you know 2 theta p, you just minus 90 degrees or add 90 degrees to get to the maximum shear stress planes. Okay, this is again showing you how you can draw the diagrams if you want to, with the points relating to all the location, okay, on the graph. So first step, if you want to draw, is to establish the coordinate system. So there are two ways doing Mohr circle. One is to use a graph paper. The other one is just to sketch on a plain paper. So if you draw using a graph paper, you use accurate uh, axes, accurate lines. So you have to use drawing tools to aid you. And also you use the scales for X and Y axis, or the normal stress and the shear stress axis. You use the same scale for both axes. So you need to determine where the axes are, right? So for the horizontal axis or the normal stress, that's not a problem, just put in the center of your graph paper. But for the vertical axis, which represents tau, the shear stress, you have to be careful, because you need to determine whether the graph is going to be on the right of the axis, like our previous example. So we can have, what we can have is, we can have Mohr circle somewhere over there, or somewhere over there, both negative, or everything is negative, or somewhere intersecting the origin. So knowing approximately where your Mohr circle is will help you to determine where you want to place your shear stress axis. Is it in the middle of the graph paper? Is it to the right of the graph paper? Or is it to the left of the graph paper if your circle is on the right? Okay. And the other thing is your scale for the axis. Okay, this is normal stress, this is shear stress. The scale that you use for this axis, you have to determine carefully so that you don't get a circle which is too small, that will reduce the accuracy of your reading from the graph, or you don't want the scale to be too large, such that when you start drawing the graph, you find that the graph exceeds your graph paper. Okay, you don't want that to happen. That is the only setback of using Mohr circle on graph paper, right? The other thing is, you can do is to just sketch, but sketching will not allow you to read the values as if you are reading a graph. Instead, it's a mix of having the graph to help you visualize what happens, and doing some basic calculation to get accurate values. The values be much more accurate than the graphs, but you have a little bit more work to do in evaluating the values. Okay, you need to do some calculation. Okay, then after determining the coordinates system and also location of axis, what you then do is you go to step 3, plot center of the circle. Now the center of a circle is just the point where you find the average value of the normal stresses. So it's sigma x plus sigma y over 2, or that is sigma average. Okay, remember that equation is sigma average. So plot sigma average point first on the uh, normal stress axis or sigma axis. Then you plot point A, or you plot either one first, doesn't matter. Plot point A, which is the coordinate for the first point, which is sigma x and tau xy. Okay, plot those points. Once you have A and C, join them together. Join point A and C. And the line AC is equal to the radius of the circle. Then using your drawing tool, with C as the center point and R as the radius, you draw a circle. Okay. So in other words, this is what you do. If when we look at this stress element here, sigma x is positive, sigma y is positive, and tau xy is a certain value, right? Now, if we try to determine from this, we will say that most probably that the circle is going to be on the right of the vertical axis or shear stress axis. It's going to be on the right. How far right depends on sigma x, sigma y, and tau xy. So you tend to draw the shear stress axis towards the left of your graph paper if you use a graph paper. Otherwise, just sketch a line, vertical line on the left of your plain paper. And then you have your horizontal axis right in the middle. Okay? And that represents the normal stress. So that's sigma. Normally we have megapascal as the stress values. Okay? So we have tau. Also we have megapascal as the unit. And this is positive downwards or counterclockwise. Okay? And so up here is clockwise or negative. So from here we see that sigma x is positive, tau xy is positive. So sigma x, so we plot sigma x. So this point A here should be sigma x, right? And tau xy is positive. So the coordinate, this point there is tau xy and it is positive. So coordinate of point A is sigma x tau xy, right? So that's the coordinate of point A. So you get the first point. Forget about the circle first. You get point A. So you get this point here. Then you plot point C. Point C is equal to the average normal stress. Okay? Sigma average. So you plot sigma average. This is 0. Sigma average and you get point C. It is on the normal stress axis. Then you join these 2 points AC with this horizontal with this line, and that becomes the radius of the circle R. Right? And then you use your drawing tool, C as the center, R the radius, draw the circle, and that is your Mohr circle for this problem, for the given problem. Right? And the rest is doing whatever you want to do with the Mohr circle, as I have explained before, what a Mohr circle can do for you. Right. So point A here is your reference. So this is your reference, or in other words, this is the x-axis location. Okay. All angles are twice the actual angle. So all angles in Mohr circle is twice the actual angle. Now point B represents location of principal stress 1 or maximum. Point D is the minimum value. So you have coordinate here is sigma 1 or sigma maximum and 0. Coordinate for point D is sigma 2 or minimum stress and 0. Right? And then we have E. E is the maximum value for shear. Coordinate is sigma average tau max. And F is the other location of the plane where you have the maximum shear stress. So the coordinate is still sigma average, but minus tau max. Right? Now someone might ask me, sigma 2 shouldn't be negative. Yes, it could be negative if it goes to the left of the shear stress axis, because that's 0, right? Now if your circle goes to the left, sigma 2, the value is 0, but normally we just write it as sigma 2. Okay? Just write as sigma 2. Similarly for sigma 1. Right. So since BC represents the location of the axis or the plane where sigma 1 occurs, the measurement comes from our reference, which is AC. That's the reference axis or x-axis. All the angles can be measured from there if you want to. So we have 2 theta P1, y is written as 1, P1 because this is sigma 1. Okay, the first principal stress, maximum normal stress. Okay, and the angle at the bottom here is written as 2 theta S1 because that location for CE. CE is the plane where you find the maximum shear stress in the positive direction. Okay. Now this is the second approach. Instead of plotting point A and point C, what this does is you plot what you call point X, because point X refers to the x-axis. So it's simpler for you to relate. Okay. First you plot point X, and point X is sigma X and tau xy. Now forget about the minus because this is another textbook, not Hibbeler. Now that textbook has a different sign convention. That's all. But let's call this clockwise and this is counterclockwise. Therefore, this value then becomes positive if it is counterclockwise, right? And this one becomes negative if it is clockwise. Okay, so we plot point X and Y. Remember our stress element, we have point X and point Y. We have X and Y based on the diagram below. So sigma X and tau xy in the positive direction represents x-axis. So we have sigma X, tau xy. Okay. And point Y is sigma Y, tau xy, but clockwise or negative. So we plot point Y. So we have point X and point Y here. So we have point Y, we have point X, right? Then you join the 2 points, X, Y. Of course, if you draw a graph, you can join just a straight line and intersects at point C. And point C is the centroid of the circle. Okay? And then again, use your drawing tool and draw the circle with C at the centroid. So you get the same thing. But here you have 2 lines. CX represent the x-axis. That's the x direction here, right? CY on the left, or BC, not BC, CY represents the axis Y here, or represent the plane, which is the top plane of the stress element, right? A represent the principal stress axis, and B is the principal stress axis too, but it's the minimum normal stress. And A represents the maximum normal stress. Again, the rest is the same. How you read or how you use the Mohr circle is the same. Okay, so that is again a Mohr circle. So what we then have is, for example, if you look at this circle here, now this is your reference, that's x-axis, right? A is maximum value of principal 1, so there is sigma 1 or sigma max. From here, you go up or you go counterclockwise, that's 2 theta p1. And so from x, you go counterclockwise, theta p1. And you will get the stress element where you have principal stresses only. So you have sigma max, sigma min, okay, and no shear stresses. If you go from the reference, that is the x, clockwise, 2 theta, you will arrive at a point here, okay, a point x prime. And you draw a straight line across, you get y prime. So you get these 2 points here, x and y. Now what it says is, if you want to find the normal stress on any plane, any inclination, any angle, just do that. You want it to be clockwise, theta. Therefore, in the Mohr circle, draw 2 theta. And then you get this line, draw the line. You have a graph paper, then you just read the value of the coordinates. If you don't, then you have to do some calculation, okay, based on geometry. So we just draw clockwise from the reference, angle theta, and we get a stress element. So what are the values of the stresses on the stress element? Comes from the coordinate of the points. That is x prime and that is x prime. The coordinate of the x prime point is equal to the stress values here. So you have a sigma x prime and tau x prime y prime. If it is positive or counterclockwise, this is counterclockwise, right? This is positive in our case. So you draw is counterclockwise. Over here, this is negative or clockwise direction, right? Clockwise. So you draw clockwise components of the shear. Okay, clockwise direction. And then the normal stress on this plane, y plane, will be from this coordinate here. So it's sigma y prime. So just put sigma y prime there. Okay, that's how easy to look at Mohr circle to determine stress analysis. But of course, if you do sketches like this, you have to do some basic calculation using geometry theory. Okay, just geometry that you have learned. Now, a little tips on Mohr circle for plane stress. If, for example, we have only axial loading, like what we discussed early in our lecture for this chapter. Now we only have axial loading. There is this force and this force here, right? P through the axis in the x direction. So there is the x plane and there is the perpendicular direction is the y plane. Now you see that when we do calculation for the right hand plane, we only have sigma x. Okay, we do not have sigma y. Sigma y is 0. You also don't have any shear, right? Axial loading, you don't have shear in the normal section, normal to direction of the loading. So when we plot Mohr circle, what we get is sigma x is that, and sigma y is 0. So sigma y is right on the origin of the graph, okay, where the two axes intersect. So that is 0 point. So we only have x and y. And so we can conclude that we have principal stresses in that plane. Okay, so sigma x now is the principal stress maximum value in this case, and sigma y is the minimum value for principal stress or minimum value for normal stress, and it is 0. Any other point on the circle represents stress condition on a plane in certain direction. So if you say I have this point here, you draw a line to that point. That line represents direction of the plane from the reference. So if x is reference, it goes clockwise, right? To theta. And the coordinate here is the stress. So it's sigma x prime, tau x prime, y prime. That is the stress condition for that plane. Now, of course, stress element, you have a square. Therefore, you extend this line on this side, right? So you get sigma y prime, tau x prime, y prime. And of course, it is negative value for the tau. Okay. Now, the other thing is, if you look at just pure torsion, the first one is purely axial loading. The second one is pure torsion. You only have torsion. You do not have any other external load. Just torsion. Now, if it's torsion and you draw or you take a stress element, we find that we only have shear stresses on the surface in the x and the y direction. Only shear. No normal stresses there, right? So the direction of the shear stress on this right hand face depends on the external loading applied. If the external loading is going in this direction here, if you imagine on this side is going upwards, right? At the back there, it seems to be going downwards. So here on the right is going upwards. And upwards is positive tau. On the left is going downwards. So forget about that. But on the top here is going to the right. And if you change this into x prime, then it is going downwards. Or in other words, the couple on this vertical plane here are counterclockwise, and the couple on the horizontal plane is going clockwise about the centroid of the element, right? So if you plot, sigma x is 0 and tau xy is positive. So if we plot, we are plotting actually this point here, x, and the coordinate is 0, tau, xy, which is positive, right? And if we plot point y, we have 0, no normal stress, and the tau xy is minus tau xy value, okay, because this is clockwise, and at the bottom is counterclockwise, right? So that is your reference now. The principal is given by point A. That's the principal stress, and also point B, right? Point A and B. So if you look here, the difference in angle is 90 degrees. Therefore, you know that the axis or the plane where principal stress occurs will be 45 degrees on the actual object outside. Okay, it's 45 degrees. Right? So that's the tip for you. You have to remember those clues. They are very important to help you solve your problems in test or examination. Okay, this is an example of using Mohr circle. That is the problem. Now, if you look at the problem here, you have normal stress is 50 to the right, right? So its tensile is 50 positive. So this is sigma x is positive. Tau xy is upward, so it's positive tau xy. So tau xy is positive as well. Sigma y is negative, is compressive, so that is sigma y. And tau xy for the y plane is clockwise. The couple is clockwise for the horizontal surfaces or negative, right? So this is the same example as before. So you draw more circle. What you then draw is, first you plot point x. Point x is 50, right? 50 and 40. So point x is 50, 40. It's shown here. That is sigma x. That is tau xy. Is clockwise. Sorry, it's counterclockwise. So it's positive downwards or counterclockwise. See the arrow here? The arrow shows direction is counterclockwise. Right? So that gives you point x. Point y, sigma is negative 10. And tau is 40 clockwise. So you have negative 10 will give you sigma y. And 40 will give you tau xy is clockwise. So it's upwards or negative. Right? So you get point y. Okay, so we have point x and point y. Join the 2 points together, you get point C in the center, and you draw a circle which will straddle both point x and point y. Now this circle represents state of stress at various orientation of the stress element. Okay, so we have the circle now. And from the circle, we know maximum normal stress or principal stress is given by point A and point B. Okay, so point A and point B will give you maximum normal stress. So that will give you sigma 1 or sigma max and 0. That's the coordinate. And point B will give you sigma minimum of sigma 2 and 0. That's the coordinate. Okay. Now, if we sketch, you can do calculation to find the values. Remember Pythagoras Theorem and all those things, sine rules or cosine rules for triangles. You have all those things. So you can determine from geometry. So from geometry, we know that point F is sigma x or 50. Point C is the average value of the normal stresses, which is 50 minus 10 divided by 2. Right? So it is 20. So that's sigma average. If that is 20, that is 50. So it is 50. This is 20. So the length CF will be 30, right? If CF is 30, Fx is 40. Remember? That's tau xy. So that is 40. So the hypotenuse will be easily found using Pythagoras theorem, right? So you use Pythagoras theorem. R or Cx is equal to square root of 30 square plus 40 square, or you get 50 megapascal. So now you know R. That's the radius of the circle. You know the center. Center is CF. Sorry, not CF. Center is OF. I normally write it as OF. The length here is 20. So what we have is, we have OF as 20. Yeah? OF is 20 megapascal. Right. So principal stress, you can find from the location of point A. So it is equal to OC. OC is 20, right? OC plus CA, or this is the radius, okay? And you know the radius is 50, which is equal to CX, okay? R, CA is equal to R is equal to CX. We have calculated that. That is 50. And so we can easily find sigma max is 70. Sigma minimum, this is typo error. This should be minimum, not maximum. Okay, so that is sigma minimum. Right? Sigma minimum is equal to OB. This is O, and that is point B here. So it's from O, the centroid of the axis, okay, where it intersects, that OB. Now OB is equal to OC, right? OC is to the right, minus R, because CB is R. It's the radius of the circle. So it's OC minus BC or R again, right? So it's 20 minus 50, so we get minus 30. And that's how you get sigma max and sigma min easily. Okay? Now to find the direction or location of the principal plane, we need to find the angle. Now we know that AC represent the plane for principal 1 or maximum normal stress. It is located counterclockwise from our reference X. So how do you get this angle here? Can you find the angle? You use either cosine rule or tangent or whatever rule you want to use. Okay? So we can say tangent of that angle there is equal to fx over cf. Okay? And that angle will be twice actual angle, remember? So that is 2 theta p1. So tangent to theta p1, so we can just put 1 there if you want to. Tangent to theta p1 is fx over cp, so it's 40 over 30. Therefore, 2 theta p is 53.1 or theta p is 26.6. It is counterclockwise in Mohr circle. Therefore, in actual situation, it is also counterclockwise. Okay, just using the angle 26.6, and you get the principal plane direction. Now that is the plane where you have the maximum value, because that is sigma max. Okay, and so the other plane will give you the minimum value, sigma b there. So you have sigma minimum there, sigma max and sigma max over here. Okay, that is how we use Mohr circle. Now, if you want to find the maximum shear stress, again it's the same rule. You can go from A if you want to, from the plane for principal stress. It is 90 degrees away, right? To get to the top point D there. And top point D here will give you sigma average and tau maximum. And this tau maximum is clockwise or negative in our case, right? So from principal plane to go to the maximum shear stress, we go counterclockwise 45 degrees. Remember, this is going counterclockwise angle. This is also counterclockwise. So you get to this point here, right? And so on that plane there, the plane towards D, you will have these stresses there. The average normal stress and tau max is negative or clockwise. Okay, that it shows you is clockwise. So you have a clockwise direction for maximum shear stress. And for the other plane is just complementary. Okay, it's just opposite direction. Now, however, if we were to draw towards this side, instead of going there, we go here, x2 prime. So from here, we can go 45 degrees, 45 degrees clockwise, meaning we are going from here to there, right? 90 degrees. So we reach point E. So it's the same thing. So if you draw your Mohrs circle, you draw your stress element, remember, it looks the same as this one on top. And then you have your average, sigma average, you have your tau max, and sigma average. Okay, you have all the same thing. So it's tau max. Now if you draw carefully, you'll find that this and the one up here, they are the same. They are the same stress element. Right? So that is how we use Mohrs circle to help us determine the principal stresses, the planes or direction of the stress element where they occur, uh, direction for maximum shear stress planes, or orientation of the stress element, and the values of the maximum shear stress and principal stresses. Right? So that's how you use Mohrs circle.